This is the lecture for Module 2A of Unit 3. This module concerns calculations involving first and second order reactions. Let's look at first order reactions and first order rate laws. A first order reaction has the form R equals Ka, where A is the reactant, some reactant. In other words, the rate depends on the reactant concentration to the first power. In that case, it can be shown that if we multiply the rate constant K by time, where the reaction starts at some time 0, then Kt will be equal to the natural log of A0, the starting concentration, divided by At, concentration after time elapsed. Again, the starting time is 0, the final time is t. So we anticipate, since A is used up as reaction goes on, that At is smaller than A0. You'll often see this law is written natural log of A equals natural log of A0 minus Kt, which is just a rearrangement of this equation, really. Now, in a first order reaction, the half-life T sub 1/2 is when concentration At is half A0, or when half the starting material has been used up. The natural log of A0 over At would be the natural log of A0 divided by 1/2 A0, and that equals K times the half-life time T 1/2. You could show by canceling A0s with this in this expression and then dividing, that this means the half-life time is natural log of 2 over K. In other words, in a first order reaction, the half-life is a constant number that does not depend on concentration. For example, consider this reaction, which is first order under some circumstances. Cyclopropane, this material, goes to this material, propylene. K is 1.1 times 10 to the negative 6 reciprocal seconds. You will see that first order reactions have reciprocal time units. And we'll assume an initial concentration of cyclopropane of 1 times 10 to the negative 2 moles per liter. Determine the concentration after 24 hours. Now, you should be able to stop and attempt this problem before going on. If we use the equation natural log of A is natural log of A0 minus Kt, where A is concentration at time t, then the natural log of A is the natural log of 0.001 minus 1.1 times 10 to the negative 6 reciprocal seconds times t. We know the time is 24 hours, but since the rate constant is in units of reciprocal seconds, this is a clue that we will need to work with seconds as our unit of time, so we multiply by 60 to convert to minutes, and then by 60 again to convert to seconds. The elapsed time is 86,400 seconds. And inserting that into the equation for the natural log of A gives natural log of A is natural log of starting concentration minus K times T. Note units cancel here. So this is unitless. And we obtain the number negative 7.003. Taking the inverse natural log gives a value of A of 9.09 times 10 to the negative 4 moles per liter, or 0.000909. Now let's look at an example using the half-life. Here is an example from radioactivity, carbon-14 dating. You will see, well, here and again, when we learn about radioactive decay later in the course, that all forms of radioactive decay are first-order processes. You may have heard that the decay of carbon-14 is useful for dating material. Carbon-14 is detectable in material and is a radioactive substance that decays with a half-life of 5,730 years. Alright, so suppose wood from a temple in Okazaki, Japan is found to have 69% of the carbon-14 found in living trees. One could ask, how old is the temple? Alright, now implicit in the question is that there is a certain concentration of carbon-14 in living things, corresponding to the fraction of carbon-14 on the planet at the time. And that when something dies, it is cut off from the life cycle process, and the carbon-14 within it begins to decay. So 69% of the carbon-14 is remaining from this temple wood, which is in this problem. The implicit assumption or hint on how to attempt this problem before going on is to assume that the concentration is 69% of what it was before. In other words, the final concentration is 69% of the initial concentration. Alright. We'll let A naught be 1. 1 what is not so important. 69% of that is 0.69, and the natural log of A naught over AT then is 1 over 0.69, and that's equal to KT. Now if the half-life is 5,730 years, we have a half-life formula, K is natural log of 2 over the half-life, that allows us to solve for K if we know the half-life. We get a rate constant of 0.000121 reciprocal year. Units of reciprocal year, as you will see, are alright for the rate constant in this case. And we won't need to convert to seconds. Right, if we divide the natural log of A over A naught by T then, 1.69 by K then, I should say, we obtain the time, and solving for time gives us 3,070 years to 3 sig figs. Now let's examine second order reactions. Here the rate, correcting a typo, is equal to the square of the reaction concentration. We can show that when the rate law is second order, depends on the square of the reactant concentration, that this formula relates time to concentration. Here we have 1 over A, where A is concentration at time t, minus 1 over A naught is equal to KT. Alright. Since A gets smaller as time goes on, 1 over A will be larger than 1 over A naught, and we have positive numbers on both sides of this equation. Alright. Consider this before and attempt the following before going on. HI reacts to make H2 and I2. The reaction is second order. Assume an HI concentration of 0.02 molar at T equals 0. Remember, at our starting time, T is 0. Here is a value for K. Note that K has units of liters in the numerator and mole times second in the denominator. You will see that these are the typical units for second order rate constants. And consider two questions. What's the half-life of the HI or hydrogen iodide under these conditions? And when will the concentration of HI have decreased to 0.0032 molar? Now, I think you should be able to attempt the following before going on, or to attempt this problem before going on. Alright, here's the solution. At T equals 0 again, HI concentration is 0.02. Here's our value of K. To find the half-life, well, half-life is time when half is gone. So, when half is gone, the concentration would be 0.01. So we take 1 over 0.01 minus 1 over 0.02, and that must be equal to KT. We know what K is, so we could solve for T. Alright, now in general, you will see that K times the half-life, T1 half, is 1 over the initial concentration. In general, as I was saying, part of the interruption, you will see that K times the half-life is 1 over A sub naught. In this particular case, if we take this difference of concentrations, divide by the rate constant, we attain a time of 31,300 seconds. Divide by 60 to convert to 522 minutes. To find when HI will be 0.0032, we insert 0.0032 for the concentration at time T. Take the difference of inverse concentrations, divide by K, and we'll find a time of 164,000 seconds. Or 2,730 minutes. This concludes the presentation for Module 2A of Unit 3.